was asked by François to give an introduction or a tutorial on network calculus. So that's what I'll try to do in a few minutes. Network calculus is used primarily today for the analysis and the validation of time-sensitive networks. What are time-sensitive networks? Those are networks that are built with the same hardware as we know, internet switches, routers, etc. But the needs are different. What we require to have what is called deterministic service, which essentially translates into the fact that we can guarantee worst case delay variation or delay filter, and also what is called zero congestion loss. So you can never guarantee that the packet is not lost because it has a transmission error. Nothing you can do against it, but you can guarantee that there is no congestion loss, which means in particular that we don't do congestion control like we do with TCP, quick in the internet. This is not an option for such networks. And in particular, we need also to have proven bounds. So it's nice to say that we have guarantees. Now it's showing up in the middle. Voilà. In particular, in settings like aerospace, where this has been started for the first time 15 years ago, there's a need for certification, which means the bounds that you compute must be proven and verifiable, ideally by computers or semi-manually. This is used, as I said, in aviation, today also in modern cars. This is an example of the Volvo car network. Is being deployed in the most modern Volvo car. This is also used in cellular telephony front haul networks, in the part of the network that is wired and that's sitting between the base stations and all the processing in some parts of networks that do a lot of baseband processing offloaded from the base stations. This is standardized by ITU for this context of front haul networks, but the most known standards are IEEE for layer 2 networks, and where the name is called time-sensitive networking. That's the name of the IEEE standard for that. And for layer 3 networks at IETF, and then the name is deterministic networking. More or less, at least from an academic viewpoint, both names are synonyms. In terms of standards, they're a bit different. How can a network offer a deterministic service? Well, for this, you need two things. You need first to put limits on the sources, so you don't do congestion control a la TCP. So you must limit the sources by what is called a T-spec in IETF terminology, in network calculus or arrival curve constraint. I'll say a few more words about this in a few seconds. And second, you need that the nodes offer a guaranteed service. It's the combination of those two things that can make end-to-end guarantees. There are essentially two classes of such networks. There are the synchronous networks, which are the old-style networks. Those are the networks you find today in deployments in, let's say, pre-TSN systems that are so-called time-triggered. I'm illustrating here a diagram of how this works. You have essentially a bus, and the vertical axis represents time, and then you have a TDMA arrangement where you allocate to some processes slots, and then the processes, which are typically periodic, will manage to send the data in their slots, and you do a pre-allocation of everything, and then there is zero queuing delay in such a system. This is not the focus today. This is not scalable. It doesn't work on large-scale network, and it's really well adapted to periodic sources, but as we heard yesterday, this is perhaps not the most interesting thing today. Most real-time traffic is in fact sporadic. So this is better served with what is called asynchronous network. Asynchronous doesn't mean that there is no time synchronization, but it means that the queuing system is not synchronous as opposed to this one here. So think of these as Ethernet switches or routers that have queues, and then flows are assigned to a small number of classes, which typically correspond, not always, but correspond to different quality of service requirements in terms of delay, for example. And then at every node, traffic of a given class is FIFO. So inside a class, all packets of different flows are treated FIFO. And a scheduler is used to separate the classes. So perhaps the most widespread scheduler that's available in many systems is deficit round robin. That is dates back to the last century, but it's still very efficient. And essentially, it's a form of round robin that is a bit more accurate than round robin as weights and accounts for the fact that not all packets are the same size. TSN specifies something a bit different that's called credit-based shaper, and there's probably a zillion other variants of schedulers that therefore are able to separate the different classes. Here I'm showing 3 classes of traffic: black, blue, and red, and each of them corresponds to a different queue in every queuing system of the network. The analysis of deterministic network uses network calculus typically. So far there has not really been any alternative to that. So network calculus answers the question: given source constraints and given schedulers and given a network of those, can we find ideally worst case delay, jitter, and backlog? Very often we find bounds that are worst case within the model, that are obviously worst case because the model is only simplification of the true system. The main idea, or really idea, but the main trick that makes it easy to analyze is this modeling of flows. Flows are typically a model with what is called cumulative arrival functions, which is like the CDF of the empirical distribution of what you see on the flow, which is a wide sense increasing function. And then if you have a system that has an input, so a flow can be anything. It can be a specific flow that I'm interested in, or it can be the aggregate of all the flows of a given class that we're interested in at a given scheduler. So it doesn't, the theory doesn't say what a flow is, it's whatever you want it to be. Similarly, a system is anything that transforms such a function into an outgoing function, which is less than or equal to this. That's the causality. The number of bits that go out must have come in, so it's less than or equal to it. So that's the simplest modeling that we use. And why it's interesting to have those functions that you can see very easily with this modeling. The delay, if this system is FIFO for this aggregate, then the delay for a bit at the right of this time, you draw a horizontal line and you see when it goes out. So if you take the max of this horizontal distances, which is called the horizontal deviation between the two curves given by this formula, then you obtain the worst case delay. And similarly, if you take the L1 norm of the difference, the L infinite norm of the difference, you find simply the worst case backlog. So you can see very easily on this representation the quantities that we're interested in. Flows can be typically continuous, even though in reality data is never continuous. So this is a simplification of what we're interested in when we model things at the bit level. It's very interesting when we know, for example, there are serialization effects when flows of different aggregates are put together on the same line, and we know, for example, that the limit on how fast it can flow. So this is a type of model that is used. Sometimes we use also models that are sometimes called by C.S. Cheng marked point processes. Even though they are not stochastic marked point processes, so they're also often called packet trains, which simply gives the arrival times and the size of all the packets or the jobs here are the size of the packets. There is no need for continuity here in the algebra that we use in network calculus. Continuity doesn't play a role. Typically, functions are discontinuous when there are events. I mentioned the arrival curve. How is it formally defined? So the arrival curve is a constraint on the flow at the source or somewhere else in the network. So if I have this function that describes the integral of the data observed of the flow, an arrival curve constraint is a function alpha, which is one tenth increasing, and not satisfied that whatever you see in the interval f is bounded by alpha of t minus f. Very simple. If you have such a constraint, you can always replace alpha by subadditive closure, which means you can constrain alpha to being subadditive. Now, this is equivalent from an algebraic form into this, which is using the operator called mean plus convolution, given by this formula here. It's called mean plus because it's the one-to-one mapping of the standard convolution, where you replace plus the addition by mean and the multiplication by plus here. So, and it has many of the properties that standard convolution have. It's commutative, associative, and also transforms, and etc. So this is equivalent, trivially, in fact, to that, but this operation gives a lot of results that give a glimpse of the cube. That's the, I would say, the traditional, the historical definition. Sometimes it's more convenient to use an alternative representation that has been introduced originally by C.S. Chang, but with slightly different definitions. Now, those definitions are not used anymore. We use the standard definition of arrival curve, service curve, etc. But it's still interesting to use the mark point process definition, and it can be shown that such a constraint here for a system that is of this kind, that is a packet train, is equivalent to this. So that's a constraint that bounds the empirical distribution of the bits, and that's a constraint that lower bounds the spacing between packets. And there's a mapping which is given by the pseudo-inverse. The pseudo-inverse of the arrival curve of a white-sense increasing function is the inverse. The inverse is typically not a function, it's a abbreviation and inclusion. And if there are multiple inverses to a given value, you take simply the smallest one. But if the lower pseudo-inverse, take the largest one, you obtain the upper pseudo-inverse. So this is equivalent to that, and that's something easier to analyze. So the first part is to give a constraint on arrival, that's a arrival curve constraint, and the second part is to model the guarantees that are offered by them. And for that, the key function, the key terminology is service curve. So we say that the system, so a system is anything that transforms an input into a causal output on star, offers a minimal service curve beta, where beta is a one-sense increasing function, if this is true. So if the output is lower bounded by the mean plus convolution of the input and this function here. Which translates into this, which is an explicit form of this. Now, admittedly, this is not very intuitive, but it turns out that's a good definition. To give some intuition, perhaps, where it comes from is easy to understand if we have the concept of what is called a strict service curve. So a strict service curve, we say that a system offers a strict service curve if we have during any interval st that's entirely constrained in the backlog period. So backlog period is a period of time when the output is less than the input, so there are bits in the system that are held in the system, then the output is at least equal to beta of t minus s. So within any backlog period of duration t minus s, we serve at least that many bits. So that's the simple definition of the form of service curve. It's called a strict service curve. And for example, if I have a constant line server, a line simply that is serving packets without interruption, without scheduling, without nothing, at rate c, then that gives a strict service curve simply equal to CT. And obviously, if beta is a strict service curve, it is also a service curve. But the interest of this definition is to be more general and particularly composable. So such a definition applies only to a single queuing point. And in network calculus, we would like to apply to any abstract concatenation of service elements. For example, very often we know we don't need a detailed network calculus analysis. For example, in switching fabric, we know that switching delay is, for example, variable, but is somewhere between 1 and 2 microseconds. So we can, at least the upper bound, 2 microseconds. We can also model this with a service curve. Now, service curves can take infinite values, plus infinity. And that's an example of a service curve that corresponds exactly to saying that the worst case delay is upper bounded by capital. As I said, service curve is the key tool for capturing what an abstract form that the service provided by the network element. Here's a historical example, the priority node. So assume you have a non-preemptive priority node with 2 classes of traffic, and you're interested in what happens to each class. For the high priority node, then you see that it provides a service curve which is equal to this, which is here a strict service curve. That's not very fancy. It's simply saying that during any busy period, the work that can happen to the high priority is that it's interrupted. It has to wait at the beginning of the busy period by the rest of the low priority packet because it's not preempted. So that can be improved a bit. Instead of MTU, you can take the smallest residual part of activity in a continuous model. That's the best strict service curve you would have. And there is nothing more to say about this. For low priority, you can have similar things here. If, of course, to provide a service guarantee to low priority, you must put a constraint on the high priority traffic. There's no constraint. There is no service guarantee to low priority. So here, I'm assuming it's constrained by an arrival curve that's linear. It's one of the very often used because of the simplicity of linearity. It's also called the leaky bucket arrival constraint, because it corresponds to the debug of the leaky bucket for limiting the traffic. So if this is an arrival constraint we can be sure of for the high priority traffic, Then we can find a strict service curve for the low priority traffic. So in the worst case, what happens during any busy period is that you have to curb the amount of traffic of high priority and also found a residual packet length of the previous busy period of the low priority traffic. But that's not the best you can say use this. You will not have high delay bounds. You can find a service curve, which is not a strict service curve, so it doesn't satisfy the interpretation of strict service curve. It's a bit better. It's more complicated, so it could be right or not be right. That's the best we can say. And if we use this service curve with a priority system, we're saying high delay bounds. So I gave here a simple example of what is called a static priority scheduler, which is very often used to explain sensitive networks. Other schedulers, such as DRR, EDF, audiovisual bridging, etc., they've all been studied, and we know good service curves for now. Sometimes there are simple service curves, for example, for DRR and three classes here. One of the classes of interest, the simple service curve is the red one. For the rate latency service curve, it's linear and the market. One that makes it not particularly simple. It's not right. If you want better ones, you can have the blue one. It accounts for the fact that DRR goes by rounds, so within a round, you can have an introduction, so it's a strict service curve. And the green is another strict service curve that can be improved, we know, similar to here, constraint the components. So this is well known and is used in industrial tools for example, finding good delay bounds and analyzing configuration. Also, an important property of this definition of service curve is the concatenation, which is almost obvious if you follow the definition, because the service curve means that the output is lower bounded by the input mean plus convolution of the service curve. Since the mean plus convolution is associative, it means that if I have two service curve elements in theory, then I can use the concatenation as an abstract service curve element with mean plus convolution for the service curve property. This is used for a variety of cases, but a very standard use case is when you have, for example, a DRR scheduler on the output port of the bridge, and before that there is processing of the input, and there is also a switching fabric. We know the switching fabric can be abstracted with a service curve delta t, which is this impulse function. The DRR service curve for specifically in traffic can be abstracted by a service curve delta one here. So you can take the convolution of the two, and then you can model simply this node as a single service curve, which are the first starting point for analysis in industrial tools. I mentioned the analysis. So the analysis is based on those three nodal results, about three results, which are sometimes called the three basic network calculus results, but are very simple. And they are nodal in the sense they are results that at a single node, and node being a service curve element. So you assume you have a node or network fraction that you know provides a service curve to an input that now is constrained by an arrival curve, call it alpha, and you call DFT the output. Then what I showed before on trajectories also maps to time intervals. So if I plot here the arrival curve and the service curve, then the same vertical and horizontal deviation give upper bounds on backlog and delay on this node. So this is results for the numbers I mentioned here. Also, we can concatenate this in the sense that the output here is known, the worst case arrival curve we can put on the output depends on the input variable and the service curve. The delay bound can be improved a bit. So if we know in very practical cases, we know the rate of the server. So this can be improved a bit using the packet train formulation of arrival and service curves. That can be improved a bit on this function here, which is sometimes a minor improvement, sometimes a large one. If the line rate is much larger than the rate that is guaranteed by the service, which happens when you have, for example, round-robin schedulers, 10 classes, every class perhaps with a guaranteed rate of order of C over 10. So in such cases, you will have a slightly better. And those tools are implemented in those computations are implemented in industrial tools, particularly functions that are like this one, that are a bit complicated to describe. There are tools that are mentioned at the end of the slide, the list of tools. So this is all implemented in tools. Some of them are in academic, some of them are industrial. So I described the very basic elements, in particular per node analysis. So now you problem is to analyze a network. So there's two types of networks in time-sensitive networks. The per-flow networks is the first type. In a per-flow network, the network nodes offer guarantees to individual flows. This is the case, for example, of the old style of last century called IETF, RSVP, for those of you who know this in-serve model. This is still using, for example, MPLS backbone, where a flow is a tunnel that aggregates a number of microflows. Then each of the tunnels corresponds to one path only in the DRR scheduler, for example. So if you have this, the analysis is extremely simple because we have the concatenation property. I have a flow here that we see the service curve in every network element. Then I can abstract what the network is doing to this flow by one abstract system that has a service curve. That's the concatenation of everything. Those mean plus convolution of everything. A mean plus convolution can be computed. There are efficient tools to do it for practical service curves we're able to do. Let's apply it to a simple example here. And let's compare the bounds we obtain if I first compute what happens at the first node, followed by the second node. For a simple case given here, rate latency service curve and a fine arrival curve, we'll have these formulas. So the delay at node 1 here will be P over R plus T1, where P is the burstiness of the input, and capital R is the rate of each of the servers. So I'll have a formula like this. If I compute the end-to-end delay bound, then the mean plus convolution of those two functions is a function with the same rate, but with the latency that are added. So that's the end-to-end delay bound we find when we use the concatenation. If we compare it to the sum of the nodal delay bounds that we have at every node, we see that this is less than this. So each of those delay bounds are worst case at every node. But we see here that the worst case cannot happen together. So the worst case here is due to a burst. The way to provide worst case of the node is to have a source that will send the maximum burst at the largest possible line rate. Here it's infinite, the line rate here. So you will pay here for a delay, which is the burst size divided by the guaranteed rate of the sweep. And if you do this at every node, you will have 2 times the burst terms. But it cannot happen. In fact, the end-to-end delay does not have 2 times this. This has been known for years, and it's called a pay burst limit. Guaranteed service network. You cannot pay the burst limits at every time. Essentially, if you're very bursty at the first node will smooth out, and you cannot have it at the second node. The way to have maximum delay at the second node is to find a way to interleave the traffic here and make sure they get accumulated at the second node. So that's for per flow network. In time-sensitive network, most of the time we don't have per flow network, but we have per path. So it's FIFO per path, and scheduler, as I mentioned, will separate path. Now, if we have good service curve to abstract what the schedulers are doing, then the analysis is equivalent to separating the classes. So we can analyze one separate FIFO network model per class. Not always exactly. Sometimes, as I mentioned a minute ago, when you have DRR, you can improve the service curve of DRR if you know what the other classes are doing. So there are iterative methods that will analyze the network class here. Then, assuming the worst case for the competing classes, then we'll analyze what the competing classes are, and we'll iterate until it's done. But won't go into those details this morning. So the simplest way to think about it is that we can separate the different classes via the service curve abstraction, and then we are left with the problem of analyzing the FIFO network, single class, but the nodes are abstract nodes that offer a service curve property. So one class that is shown here, and then the only thing we know about the node is the service curve and the fact that it's FIFO. And in such a network, flows are they join and they leave. So here there are 5 flows that go together, so they are influencing each other, but they leave and go to other nodes where they merge with other flows. Analyzing such a network is actually hard. There is an exponential optimization problem that can be defined in the worst case delay. If everything is linear, the service curves are piecewise linear, convex, and the arrival curves are piecewise linear, concave, then it becomes a linear program, but the number of constraints and variables is exponential. So it's probably not, but that gives at least a formal representation of the worst case. In practice, even for surprisingly very small network, it's completely intractable. So it's really exponentially very fast. So analyzing network with 3 or 4 nodes is really impossible. So there are suboptimal but tractable analysis that are used in industrial tools. There's a number of them that I will mention in the full page, but the most useful ones, as far as I know, are those 2 ones here called total flow analysis and PLP. Total flow analysis, originated by Schmidt 15 years ago, is based on concatenated per node analysis. So if I have a network here, if the network is feed forward, then I can start analyzing a network node that's at the edge. So at the edge, I have only fresh flow, so I can do the nodal analysis, analyze the delay and backflow bounds, and know the output percent. And then I can iteratively go to nodes that are at depth 2, 3, and 4. So in a feed-forward network, this is what it does here. It uses the per-node computation and propagates them. Most networks are not feed-forward because in networks you want to have redundancy, so you have narrow links or you have circles, and so in a non-feed-forward network you have the graph induced by flows as traffic dependencies, and this method doesn't work. But you can have a fixed point method. So there's iteration. So essentially you do the same, but you iterate. So one simple goal is to simply cut the network and take variables at the unknown quantities of the cut and then iterate them. It looks like a hack. The hard thing is to show that you obtain certified bounds. So this involves a number of technical steps that use the monotonicity of the operators. It can be shown that if such a method converges, and if we do it well, for example, we use exact arithmetic, so all the quantities are rational numbers with exact representation. Since we're talking of convergence, we'll also do some rounding. For example, we round the number of bits to be an integer. So that's such an algorithm. If it converges, it will put a factor in it. It will be a point where the computation. And if it terminates, the bounds are, if the implementation is correct, the bounds are proven bounds. They are not just a hack, they're proven delay bounds everywhere. The problem is sometimes if it diverges, we don't know whether the network is stable or not. And there is an alternative to this, which is based on exponential linear programming. That the worst case, the representation by an optimization program of the worst case delay, where we relax a large number of the inequalities. And by doing that, typically it doesn't work, so it's full of tricks. But one of the tricks is that you add the result of this analysis here. So you first do this analysis, which is fairly simple to do, it's computational. And then you use this as constraints instead of having so you remove a large number of constraints, which you replace by the result of this analysis. And you keep another number of constraints that are well chosen. And that generally provides way better bounds than this. It provides much better bounds. In particular, when you have a large depth, if flows come and merge and go through many nodes in sequence, in particular the stability region, the region where this provides finite bound, which is restricted here. So TFA is this blue line here, the PLP is this red line here, ELP, which is the worst case here, it's for one network, so the extremely small number of nodes is very close to that, or at least for the part where we can provide. So I would say that's the best you can do today, but it's limited to concave arrival curves and convex service curves, and we know sometimes this is not the best. For example, for DRR, the best service curves are not concave, so there's a trade-off between the two. This can be solved for, in theory, for any concave, any arrival and service curves, but then the optimization problem we have to solve becomes a non-convex one, so it's also an integer variable, so again, it's not tractable. So those are the trade-offs. The state of the art today. When such methods diverge, we simply know that our analysis method does not provide a good delay bound. So the question has been around, is it because our method are bad, or is it because the network is truly unstable? Unstable in the sense that there cannot exist a finite delay bound that you can convert. Cannot exist a finite delay bound, not speaking one that you can compute. So this question has been studied by Matthew and Drews, and that's really asked before. So I take here the simplest of all networks, so it's a FIFO network. single class, and all flows are constrained by regulators that are simple confined functions everywhere. But so the network is not deterministic in the sense that you allow the sources to be adversarial. The sources are trying to do things as bad as possible to make the backlogs be as bad as you need. Such a network is called underloaded, is the utilization factor. That's how you can simplify the utilization factor definition by any sources that are constrained by linear parameters, as I said. And you have servers that provide a rate latency service curve. So you can take the sum of the rates, which is the worst case rate at which the fault can produce data, divided by the guaranteed rate. So that's a figure of merit that gives you, if it's less than 1, then intuitively the network should be stable. For example, if you have a product form stochastic queuing network, if you run that, will be the same definition of rates, but for the subcritical an underloaded product form queuing network, is it stable? So here, that's the question that is asked: is this u less than 1 necessary condition? Well, the answer is no. Of course, an overloaded network is not stable. That's true. If you allow sources to send at a rate larger than the guaranteed rate, you can easily create simulations where the backlogs will accumulate with no bounds. But the surprising result is that there are unstable or underloaded networks at any arbitrarily small utilizations. So that's a theoretical result. It's constructive. Matthew and Bruce built network, but it's specific. Okay? So that means it's possible to have a network with utilization 95%. In practice, that's what we see. We see that when we do the analysis of networks with TFA or PLP, when we reach 95, 99%, we know perhaps the thing will diverge, and most of the time it does. Really. But the thing is, it may, in fact, the worst case can really, it can really be the worst case, not just the result of analysis here. Now you can think that the worst, of course, for this to happen, you need a network that has cyclic dependencies. If the network is feed forward, so then as long as it is underloaded, it is stable. Because you can do any nodal analysis from edge to the higher depth nodes here. You can think that the worst case of cyclic dependencies is the ring, but it is not. So any underloaded ring is stable. So in fact, a unidirectional ring is not posing problems. So the accumulation of burst energy in the ring doesn't play a role. In fact, if you look at those networks here, you need bypass links. So you need that some sources create a huge burst that accumulates in a network, which delays some other sources, and then this burst stops, so that the delay creates a big output burst. But this output burst needs to go not directly to the next node, but to yet another node, where it will interfere again with stability and kind of things for this instability. Now, whether it is still an open question to have good stability conditions, and in fact, we don't know today how to guarantee good stability conditions, other than by computing and seeing whether PLP or TFA gives good delinquents. Because of that, and because of other reasons, an important device that is used in such network called a regulator, in the terminology of IEEE stands for ATS, asynchronous traffic shaping. A regulator is something that enforces an arrival curve constraint, possibly by delaying packets from two. For example, here I have a flow that has two blue packets that are too close together, and the regulator will enforce some shaping, some spacing here, if the arrival curve constraints did not allow such a burst of two back to back. Okay. It's typically placed at network edge, because if you construct a network and you want to provide guarantees, even though every flow is supposed to have guarantees, you cannot be sure that it is effectively implemented. There can be bugs, simply, or if the arrival curve constraint not being followed, you have problems with hardware and software, the so-called babbling idiot syndrome, where all of a sudden the device keeps sending packets because it's caught in a loop and sends the packet again and again. So you want to protect the other flows from something. If this flow is merged with others in a class, of course, the performance guarantee for this class will not be right. So people put regulators at network edge, which are typically per flow. Another reason for that is that, as I mentioned before, in a per flow network, when there are cyclic dependencies, the burst tenderness, the worst case burst tenderness increases at every flow. if there are cycles in the dependency. So along this cycle, the burstness of flows of interest increase. But since those flows also merge with other flows at other nodes, they have an impact on another loop, and each of the two loops enforces each, makes things worse for the other. And this is one of the ingredients in Matthew and Drew's network, also to have a unbounded delay. So we can, of course, analyze such network by PIP, a solution to a fixed point, but very often we find, not very often, but depending on the topology, we cause bad delays. In fact, to the point that many industrial networks that are used today, they work very hard on routing the end-to-end flows to avoid cyclic dependency in the flow curve. Even though there are loops in the topology, we try to route the flow such that the resulting induced graph of dependencies is free of cycles, which is a huge constraint, but that has been done, for example, in AFDX and Airbus networks, etc. Because of this problem, because as soon as you try to analyze the worst case data bounds, you're not able to find good bounds. What is possible is to introduce regulators. If you put a regulator somewhere in the middle of the network, it will break the dependency. Force the burstness of the flows to be exactly what the regulator enforces. Regulators exist in the standard in two forms, per flow and interleaved. A per flow regulator, you can think of it as it handles every flow individually. So here's the example like here. The problem with the blue flow that is too vertical. So the blue flow will be delayed, but that has no impact on the other flows here. It's highly it cannot be implemented typically as a standalone device. It is implemented as a manipulation of the input here of buffer because it can have an instantaneous release of packets. Because of those constraints in implementation, what is often used is called an interleave regulator, where you do the same thing here. You manage, you look at all the flows, and when a packet arrives, you examine only the packet that's at the head of the queue. There's a single queue, and you examine the packet at the head of the queue. For example, this one is okay, it's released. But the next packet, when it arrives, it's too early, so it's delayed. But by delaying this packet, we also delay all the other packets because it's a part of the queue. So that's called the interleave regulator, and that is mostly used in TSN in the TSN standard. When you introduce packet regulators, you kill the cyclic dependencies, but the packet regulator itself is a node. How can we analyze it? Can we find a service curve for this node? For per flow regulators, we can. For interleave regulators, we cannot. But there is a theorem called a reshaping for free property that says that if I have a FIFO system with many flows, but it's FIFO globally for all those flows together, and because of the multiplexing here, it will typically change the burstness of the input flow. For example, the blue flow, which was sending one packet every spacing, for example, of at least 1 millisecond, maybe by the non-determinism of the FIFO system here, may result in more burstness of the output here. So if we put a regulator here, we will delay this packet. So this delay must be also accounted for, and also we must understand the backlog of the regulator. In terms of delay, it's very simple. The worst case delay of the concatenation of the FIFO system and the regulator that works on the same aggregate is the same as the FIFO system. So worst case regulator here can only delay packets that had a delay less than or equal to the worst case delay in the previous one. So this is the called reshaping for free property. That's also one of the physical properties of reshapers. And this is why regulators are used, because when you have them in a network, you can analyze the impact that they have on worst case delay. Essentially, you can do as if they were not present. But when we analyze the network with TFA, what follows here, you know exactly an arrival curve for each of the flows that is. Everything that I said here is assuming perfect time. And one of the projects we had with GetNet, we were asked the question, but can you, the clocks we have, so one manufacturer told us, but the time is not perfect, and are you sure about all the computations? The networks typically have clocks that are not perfect, but they are synchronized. So most networks today are synchronized with tight synchronization with accuracy of the order of a microsecond, which is for time-sensitive networks. And if I use a regulator or other systems, then all the operation of the regulator is based on time measurements here. So does the clock inaccuracy play a role here? That's the question. Well, the clock inaccuracy is captured by a number of things, but the primary thing is the drift, the frequency offset. The clock has a nominal frequency, 1 gigahertz, for example, but in reality, it's not exactly 1 gigahertz. It has a tolerance that depends on pressure, temperature, number of things, and the manufacturer. So it has, every clock has a frequency of set. That's why our watches are not exact, they deviate by a few seconds every day. That's the kind of accuracy. We can capture the requirements that are very detailed ITU specifications on the clock accuracies and all the parameters. They can be captured in a worst case envelope that says if I measure the quantity with one clock or with another one, there is those bounds between the two. Where the major factor rho is the drift. It's typically an up or down. It's a number that's slightly smaller than 1,0001, for example. Omega is the synchronization error. If the network is synchronized, then the clock different offset between two clocks is bounded by omega. If the clock is not synchronized, then omega is infinite. And we have this relation between the two, which is a mean-plus relation. It's not obvious, but it's symmetric. So if I change the role of d prime, I can exactly the same in quantities. And this can easily be compounded with all the network calculus concepts of arrival curves and service curve. For example, if I have an arrival curve that's implemented at the source here with a clock on the source, so the source forces packets to versus B and a rate R. And if I implement it somewhere else in the network, for example, at the reshaper, it will be implemented with a clock of this device, which is not exactly the same. So we can map an arrival curve seen in one clock to another curve seen in another clock, and this will give this one here, the synchronization in the synchronized network. There will be kind of thing here, which, as you see, has an arrival curve here with a slope that's slightly larger. So that's the intuition. If I say my node can send 1,000 packets every second, in fact, it can send 1,000 packets in the worst case every 0.9999 seconds, which is a bit more. And what happens if you put this in the network, where if your regulators are not adaptive, that means if the regulators just implement the phase values, then this might lead to instability because this little epsilon, in the worst case, the regulator is a bit slower than the source. So the source is sending 10 to the minus 4 more than the greater things, and this will build up all the time. So you need to put that would be in unstable in non-synchronized network. In synchronized network, this is capped by the worst case limit of the synchronization error. So there is a limit. But the surprising result is that for per flow regulators, we can analyze the per flow regulators and put it down on the effects of this. In interleave regulators, if it is not adapted, it is unstable. And we can reproduce very simple simulations, the Deterministic simulations that are publicly available with 3 flows, 1 bridge, and an interleave regulator here. So there's all following the TSN standards. And you can see that the delay increases by 100 microseconds per second of operation. So all the time that's going to accumulate, and also the delay bounds that are computed on board. This is because of the head of the line blocking property of the interleave regulator. Even if the network is synchronized, there can be short period of time where a packet arrives a bit faster for one flow, and there's this done in an adversarial way, like we did here. This can lead to an unstable behavior. So you need to address this, and the standard something to discuss this, you need to address it, but putting a safety margin, so if I put a regulator on the flow that regulates 10 kilobits per second, in fact, I should do 10 dot something, which should a little bit more. But the next regulator should also put a little bit more of what the previous did. So there's a cascade of things, so it's how things must be done. There's plenty of other bells and whistles, but Anna has already shown to me the 5 minutes left, almost 5 minutes ago. So I need to stop. Many of the devices in the network, for example, some switching fabrics may introduce packet misordering. So there is also another device, which is a reordering buffer. The reordering buffer is like the interleave regulator is not analyzed with a service curve, so it needs to be analyzed on its own. And you have also properties like if there is no loss in the network, resequencing is not free. So the worst case delay that the reordering buffer imposes to a flow can never contribute to increasing the end-to-end worst case delay. So only packets that were somehow too early that can cause the problem. If there is a lossy network, there's a different values, but we can compute the jitter, the impact on propagation of random curves. Another dimension that I will only very briefly mention is replication. So one of the goals in time-sensitive network is to avoid packet losses at all. So we work very hard with network access on avoiding any congestion-induced losses, but there may be other packet losses, and also there may be typically nodes that go down to a few milliseconds, for example. You come up again, but during a few milliseconds you lose your node. So this is handled by basic form coding, which is packet replication. So network nodes will replicate packets. For example, if you want a very paranoid network, and every source, that's the kind of thing that is used for the smart grid, substation automation network. That's a device that sends an alarm and some safety critical operations. So the alarm is sent to two network nodes, and every network node replicates it towards the destination on two paths, but also removes the, because if you do that 10 times, you have 1,000 replicates, which will kill the network. So you will remove the packets inside the network. That causes misordering, that causes extra burst tendency. But all of this can also be analyzed by the state of the object. François asked me to do one slide on stochastic, so that's what I will do, and that's the last one I'm sure. There has been some efforts to go towards what we could call quasi-deterministic, in the sense, introduce a bit of stochasticity. For example, if I have 1 million flows that are aggregated together, the network actors, the LeBan, will assume that the worst case is one of the 1 million flows that synchronize and send their birth together, which is very likely to occur. So this has been captured, for example, with various stochastic arrival curve proposals. So Florian Chuku proposes this terminology. S2BB is one of them. It says an aggregate satisfies this stochastic arrival curve if the probability, here the quantifiers are important. If for every t, the probability that the sub over S is bounded here. And you can take the same thing with different quantifiers here, and where the probability that for any SN in ET you exceed this, so those are two definitions that are being used. So this has been studied a lot. And for example, in work done a few years ago, we were able to analyze a stationary system. So assuming the flows are stationary, constrained by leaky buckets or any kind of arrival curves, but independent. And if you have some of independent things, the thing that comes to mind immediately is Hölging bounds. So Hölging bounds provide a very good bounds combined with other tricks to things like the stationary probability distribution of the buffer. This is, I would say, the easiest to obtain, but it's a bit frustrating because from a deterministic network viewpoint, this metric is not very useful. You can say, at an arbitrary point in time for my stationary system, I will not exceed this. But then I send 1 million packets during 1 hour. What's the probability that I will violate my delivery? It doesn't say the word. Turns out it's quite impossible to say something about the second statement I made, because that requires this definition, was shown by Florian Chuku, is that this cannot apply this gives trivial bounds if the process is ergodic. Because if it's ergodic, the probability sooner or later it will exceed. But there are some cases where we are non-ergodic things are interesting. For example, periodic sources with random phases. Once you choose the phases, the system will keep the same offsets always. So it's non-ergodic. The initial choice of the phases is unplayable, and that with that we're able to find good ones. So we're working on the service side. There are also a number of stochastic service curves that have been proposed, so they have the same kind of definition as this one. And if you bound the two together, you tend to find bounds that so far, for many papers that have been cited, are not very tight. So it's hard to find tight bounds. I would say that is the state of the art on the printed or the online version of the slide, which I guess we will have available in some service somewhere. I give a list, which is just a cut and paste of the Wikipedia page metric that gives all the tools that I mentioned. I would say the most successful industrial tool that's really used by the aeronautic industry, for example, is real-time at work. Another one is AutoNet, and there is also the Disco toolbox, so the three most widespread tools that implement all the calculations that I showed you. Well, thank you very much for your patience for your